Today we want to talk about Green's theorem. Let's take a look at what Green's theorem says. So let's F be a vector field. Now notice that F is going to be a two-dimensional vector field. I got an F1 times I and an F2 times J. F1 and F2, those are scalar functions. They're the components, the I and J components of the vector field F. So F1 and F2 are just functions of X and Y. C is going to be the boundary of some region R oriented such that R is on the left of C. So C is going to be the boundary of some region and it's oriented in such a way that as we're going around C, the region is on the left. So the orientation is counterclockwise in this picture. We should already start seeing shades of our fundamental theorem of calculus. We know that when we're integrating, we evaluate an antiderivative at the boundary. So Green's theorem is a theorem about line integrals. It says that the line integral over the boundary C of the vector field is the double integral of this expression. The partial of F2 with respect to X minus the partial at F1 with respect to Y. So this line integral is a double integral. This expression, partial F2 with respect to X minus partial F1 with respect to Y, is the scalar curl of the vector field F. Curl is a thing that we've seen before. We saw curl in Stokes' theorem, but that was the vector curl, and this is the scalar curl. Here we've got a simpler object. We've got a vector field, a two-dimensional vector field. So there's less going on. So this is Green's theorem. Let's take a look at an example. Let's say that our vector field is y I hat and 0 j hat. And we're going to take C as the unit circle. So what we've set up here, if we relate this to what we see in Green's theorem, F1 is just y. So F1 and f2 is equal to 0. So those are our two coefficient functions. f1 is y, f2 is 0. The partial of f2 with respect to y is then 0. And, oh, sorry, with respect to x is equal to 0. And the partial f1 with respect to y is equal to 1. So now we're going to start filling in the parts that we see in Green's theorem. Other things that we'll need are where the c is headed. So we'll also need an r prime of t for the line integral half of things. The cosine is negative sine. And the derivative of sine is cosine. So what we're going to do is we're going to calculate the line integral, find our target value, take a look at the other half of Green's theorem, which is going to be this double integral of the scalar curl. And see that these two values are the same. Let's first take a look at the line integral. So the curve C is parameterized by cosine ti plus sine tj, and this will go for t between 0 and 2 pi. So we'll have the function, the vector field evaluated at all the points on the unit circle. So here x is cosine of t and y is sine of t. So f at r of t looks like sine t times I plus 0j dot dr, which is minus sine ti plus cosine of tj dt. What's that? That's what the circle is telling us. So since the unit circle is parameterized as cosine ti plus sine tj, we're saying that x of t is cosine of t and y of t is sine of t. So I plug sine of t in for the y. And then that shows up down here. So that's our parameterization. That's our normal parameterization for a unit circle. So now we're going to turn this into a simple integral by calculating the dot product. And we'll have minus sine squared t plus 0 dt. As I'm sure you remember your integral of sine squared, if you have even powers of sines and cosines, we're going to use double angle identities to integrate. So we're going to write our sine squared as an integral of cosine of 2t. So what's going on here is double angle identities. So as I'm sure because we keep track of all of our techniques of integration forever. Remember when we have even powers of sines, that we convert those using cosine squared, is write that as 1/2 plus a 1/2 cosine of 2t, or in this case, a half of cosine of 2t minus a half. So that gets us to our antiderivative. And so we evaluate this and we end up with negative pi. So at that point, we just plug in 2 pi, plug in 0, and subtract. We'll end up with minus pi plus 0, because the sine of 2 pi and sine of 0 are both 0. Question? Integrated sine squared, you don't always remember how to do that, but there are double angle identities. So that's what we used at that point. What's that? And so we got negative pi. And now if we look at the double integral on the other side, the partial f2 dx minus partial f1 dy works out to -1. So it makes sense that we got minus the area of the circle, because the double integral of 1 is the area of the circle. So on the double integral side, so R is the interior of this circle. And on the double integral side, we get the integral over R of partial f1, f2 dx minus the partial f1 dy So we're integrating the over R just 1 dA. And so this is going to be the area of the circle. So it's a unit circle, radius of 1, so the area is pi times 1 squared, or pi, times the -1 we get from the scalar curl, we get negative pi as well. Question? How's everybody okay? So Green's theorem is also in that category of integrating by looking at an antiderivative at the boundary. Here we have this scalar curl over some region, and we're evaluating the vector field kind of sitting as an antiderivative at the boundary of the region. So it has that same feel to it. Integrate by evaluating some kind of antiderivative at the boundary. Has that same feel. has that same feel of our original fundamental theorem of calculus. We integrate the derivative at all the points on the interval by looking at the function at its boundary. F is the antiderivative of f prime. So this fits in that mold of fundamental theorems. Any questions? Comments? Think about the fundamental theorem of calculus for line integrals. Or a vector field is a gradient field. So let's integrate over C, where C is the any path from P to Q. So what we're looking at in Green's theorem is a curve where P and Q are the same point, because we're making a loop that encloses a region. So in Green's theorem, P is equal to Q. In Green's theorem, P is equal to Q because we're enclosing a region R. The point P and the point Q are the same. So if we apply, if we look at the fundamental theorem of calculus for line integrals, if we have a closed curve and we integrate a gradient function, we're going to get 0. So if we apply the fundamental theorem of calculus for line integrals on a closed curve, starting and ending at the same point, we'll end up with 0 on the fundamental theorem of calculus for line integrals. So f at q minus f at p is going to be 0 since q and p are the same point. It could be a p or a p because they're the same point. Yeah. So if we think about how this shows up in Green's theorem, in Green's theorem, if f is a gradient field, then this is going to end up being 0. If f is a gradient field, then the integral over c of f dot dr is going to be 0. So what that tells us, based on Green's theorem, if we have a gradient field, then the scalar curl must not equal, it must equal 0. So what we're going to conclude here this is a similar question that we've asked before. We can determine if a vector field is a gradient field by trying to find a potential function. Here's another way to determine if a vector field is a gradient field by looking at the scalar curl. So the scalar curl is going to give us another way to determine if f is a gradient field. Take a look at the partial at f2 with respect to x minus the partial, and the partial at f1 with respect to y. If those two are equal, then we have a gradient. So if we look at the calculations that we had before, if we just look at this, if we look at the vector field f as yi plus 0, the vector field yi plus 0j, partial of f1 with respect to y is 1, partial of f2 with respect to x is 0. These are not equal, so f is not a gradient field. We already knew this because we worked out the line integral. We already knew that f was not a gradient field because when we worked out the line integral, we did not get 0. So we already knew this because we calculated the line integral of around the unit circle of this vector field, and it didn't come out 0. If that was a gradient field, then if we calculate a line integral around a closed curve, we would have come up with 0 because the starting and ending points would have been the same. Any questions? Comments? Any thoughts? How's everybody okay? Everybody looks so stoked to be back on campus. I might be exaggerating that a little bit. I don't know. It's like this continuum of happiness. And with all the masks on, I can't see it. So I'm just pretending that everybody's like happy to be there. You know what I mean? All right, so some things that you'll want to notice is that the assignments have due dates on them now. I thought I had put the due dates for the remaining assignments at the beginning of the semester. Then I looked today, it's like, oh, I wonder how the vector calculus is going. It's like, oh, well, shit, I have not posted any due dates. And so they tend to not, I think those assignments don't show up on the assignments tab, they only show up in the modules. So if you're looking up in the assignments tab, don't panic that a bunch of assignments had showed up. They were already there in the modules. They just weren't in the assignments list because the assignments didn't have due dates. But the assignments have due dates. The first due date is assignments from chapter 16. Those are showing up in, those are going to be due next Sunday, and then the 10th, and then another round the 17th, and another round the 24th. And then we'll decide what fundamental theorems of calculus problems we can look at, we want to look at for homework for the rest of the semester. Good question. On the quiz front, we need to write some quiz problems so that they can be like, they can stand in as our tests. We're not going to have any in-class written tests because there are some folks that can't even make it into class. So we're just posting tests in the form of quizzes on the Canvas. So you do the quizzes on Canvas, you submit them, eventually I'll score them, and then you can resubmit them to make corrections. And that's how we're going to play the Calc 3 game. Any questions? How's everybody okay? All right. So I know we're all excited to be back. I hope you had a restful spring break. I hope you didn't do very much math over spring break or any other class over spring break. That would defeat the purpose of it being a spring break. It's supposed to be a break. All right, that's going to do it for today. I'll see y'all on tomorrow, but have a good day and thanks for playing.